In the first part of this video, I talked about what earthquakes are and how we measure them. In this second part, I'm going to talk about earthquake impacts, forecasting, and how we minimize the damage from earthquakes. I want to talk about some other impacts that earthquakes have on us and our surroundings. Probably the first impact from an earthquake that comes to mind when you say the word earthquake would be structure damage or collapse. This occurs due obviously to the up and down and the side-to-side motion that's caused by the different wave types that we just talked about. And again, it causes structures to collapse or to be damaged or destroyed. During the 1989 Loma Prieta earthquake in San Francisco, this 2-story highway collapsed in Oakland, and people were killed. And so one of the results of this is, stricter building codes, ensuring that the structures that we build are more earthquake safe. Nothing is 100% earthquake proof, but we can do our best, engineers can do their best to construct structures that can withstand earthquakes, especially in places like the San Francisco Bay Area. Fire is also a really huge impact of earthquakes, especially in densely populated areas. Lamps, stoves, candles, power lines, these can all be knocked over during an earthquake and can start a fire. And those fires can be fueled by ruptured gas pipelines or oil tanks, water lines in a densely populated place like San Francisco, which is pictured here. This is the 1906 San Francisco earthquake, and you can see that it was really badly damaged by a 3-day-long fire. And these fires couldn't be put out because the water lines had all been damaged and firefighters had no water to douse the fires with. So fire is an extremely dangerous result of earthquakes, again, especially in these densely populated areas, these cities. San Francisco essentially had to be rebuilt after that 1906 earthquake and the resulting fires. Another impact from earthquakes includes what we call liquefaction. And this is when you have water-saturated sediments and you shake those up. You can do this as an experiment at home. You can get a tub or a bowl, fill it with sand and some water. And if you place an object in your wet sand and you give that tub a shake, you'll see that object sinks in. It's essentially creating quicksand, and your object will sink. This is what liquefaction is doing. It's essentially suspending the grains in the water, and they're no longer supporting each other, and they're not supporting whatever is above it anymore either. So you can see here in this picture in the top left that these buildings, these apartment buildings, I believe these are in Japan, these collapsed because of liquefaction in the sediment beneath them. In images B and C, this is in New Zealand during the 2011 earthquake in Christchurch. There's video online, which I'll send you all a link to it. You can actually see these sand volcanoes erupting, and you can see this car it's basically sinking into the wet sediment. And what's happening here is, again, liquefaction, but more importantly, you have sandy layers that were overlain by muddy layers. And when the earthquake hit, it caused cracks in those upper layers, and the sand, which was wet, became less dense and sort of rose to the surface as these sand volcanoes, these wet, sandy sediment volcanoes. It's pretty dramatic. Again, I'll pass along a video so that you can, or I'll link it in the description below as well, so you can see what these sand volcanoes look like in real time. They're pretty wild. Another impact of large earthquakes, especially ones that occur in subduction zones, are tsunamis. Tsunami is a Japanese word for harbor wave, and it's essentially a large wave that's produced by large displacements, vertical motion of seafloor, or in some cases, the bottom of a large lake. Tsunamis are most commonly, like I mentioned, generated in subduction zones with earthquakes that are larger than a magnitude 7. And essentially what's happening in these scenarios is you have a subducting oceanic plate, either beneath continental or oceanic crust. In this illustration, you have continental crust overriding the ocean crust. And this zone right here where those two plates meet, it tends to become locked, and those plates actually aren't sliding smoothly past one another at all times. They sort of become stuck every once in a while, and then that stress is released in an earthquake. So at that location there, something that happens is you get this elastic rebound of the overriding plate. So it kind of, this part of the accretionary prism gets sort of pushed down and down and down along with the oceanic plate. And then when the earthquake ruptures, it bounces back and lifts up the ocean water above it. And that's what's causing this large wave to form. And you might get what we call a near field tsunami, which is the wave that bounces back toward the nearest coast. Or you get a far field tsunami, which is the wave that goes towards the other side of the ocean. So in other words, if we get a large earthquake in a place like Japan will experience potentially a near field tsunami, and we on the west coast of North America could experience a far field tsunami as a result of the same earthquake. So 2 tsunami waves can be generated by the same earthquake. Finally, I want to talk about forecasting earthquakes and minimizing the damage caused by earthquakes. So a lot of people are concerned with predicting earthquakes. It turns out that earthquakes are impossible to predict. We just don't know when that stress is going to build up enough for the rock to slip or that fault to rupture. But what we are working on is forecasting the probability of large earthquakes in places where they are pretty likely to occur, like the San Francisco Bay Area, which you can see here in this map. And so this is an example of earthquake probability forecasting. You can see that the faults in the Bay Area, the major faults, are all highlighted, and they have a probability associated with them. And that probability is how likely a magnitude 6.7 or greater earthquake would be between the years of 2014 and 2043. So, for example, I grew up very near the Concord Fault, and the likelihood of the Concord Fault experiencing a large earthquake is about 16% in the range between 2014 and 2043. So, overall, the probability of the San Francisco Bay Area experiencing one of those large earthquakes greater than a 6.7 is 72%. So that's pretty high, but it's something that people who live and work in that area should keep in mind. Or if you're considering moving there, that's something that you want to think about. Something that we do have, though, is an earthquake early warning system, and a few of these exist. One of the major early earthquake warning systems is called Shake Alert, and it was developed by the USGS and some university partners like the University of Washington. This early warning system it operates throughout the West Coast, and what it does is it basically detects P waves, and once the beginning of that earthquake is detected by seismometers, an alert is sent to people nearby. So even though this alert is being sent after the earthquake has begun, it should give people a few seconds to prepare themselves, to get into a safer place, to duck under a desk and hold on. And that's the goal of these early warning systems. They basically are designed to prepare people for the more damaging S and surface waves that come later. Obviously, the further that you are from the epicenter of the earthquake, the more time you're going to have between those primary waves and the S and surface waves. But even so, a few seconds can make a huge difference. These alerts are triggered again by this USGS Shake Alert system, and then that message gets sent out through different distribution partners, including the same people who send out Amber Alert notices on your phone, so that really terrifying sound that your phone makes when there's an Amber Alert. You can also get an early warning for an earthquake that same way. You can also get alerts through various apps that you can download that are all triggered by this Shake Alert system. Another way to minimize damage from earthquakes is obviously to just learn about the risk, especially if you're considering moving to a place where there might be earthquakes, or perhaps you are traveling somewhere. It's good to do a little bit of research on what the risks are in that location. Is there an earthquake risk? How high is that risk? Is there a risk of tsunami? That's something else to consider. And also you want to have a plan at work or at school or wherever you are. You should, if you live in California especially, you're probably familiar with drop, cover, and hold on. That is sort of our plan if there is an earthquake, is to drop, get down low, get under a piece of furniture, and hold on until the shaking stops. So the education in our schools around earthquakes and practicing these earthquake drills in places like where we are, that can be really beneficial and really helpful for minimizing the damage caused by earthquakes. Obviously, one other way to prevent the damage from earthquakes is to construct safer buildings. So some ways that engineers have done this in the past and continue to do this is by building buildings that have wider bases and narrower tops. Those types of buildings tend to be a lot more stable during earthquakes. They also will reinforce buildings with cross beams. And I've even seen some videos, and I'll link this down below, but there's some awesome videos about how engineers have put rollers or springs underneath buildings to absorb the vibrations of earthquakes. And so some of these really tall buildings are actually on rollers and will move side to side during an earthquake, and a lot less damage will be done on the interior. In addition to constructing safer buildings, we also want to reinforce existing structures. One of my favorite examples of a structure that has been recently reinforced because of earthquake hazard is the California Memorial Stadium, the football stadium at UC Berkeley. The stadium was built in 1923, basically right on top of the Hayward Fault, which is one of the more active faults in the San Francisco Bay Area. And because it's such a historical structure, they didn't want to just move the football stadium to a new location. Also, there really wasn't a place for them to move it to. They decided to renovate and retrofit the stadium to make it more earthquake safe. When it was initially built, the stadium was built in two pieces, so that it was basically two pieces with these expansion beams in between, so that as the fault slipped, which luckily the engineers knew that the fault was creeping about 1.2 millimeters a year, it would allow for displacement in the football stadium. So some of that displacement is actually visible on the outside of the stadium. You can see here, this was before they renovated it, that one side of the stadium has been displaced against the other side of the stadium. So in 2010 and 2012, UC Berkeley spent $321 million retrofitting the Memorial Stadium. And they actually ended up cutting it into multiple sections, put those sections on sand so that if the area were to experience a sizable earthquake, those pieces of the stadium would move independent of one another, allowing it to withstand larger earthquakes. In this lesson, I talked about earthquake impacts, how we forecast earthquakes, and then how we minimize the damage of earthquakes. I hope you got something out of this 2-part series on earthquakes, and I'll see you in our next lesson.